Assalamu alaikum and good morning. Today we're going to start with a new topic still under physical chemistry, and this topic is called the rates of reaction. It's your topic number 8. Rate of reaction comes under the bigger group called reaction kinetics. Basically, whenever you hear the term kinetics, you should automatically think about it being a study of the rates of chemical reactions and the factors that affect the rate at which the products are formed, or the rate at which reactants are used up. So basically rates of reaction and the factors that affect it. Okay. The first learning objective that we are going to look at is explain and use the term rate of reaction, frequency of collisions, effective collisions, and non-effective collisions, or sometimes called ineffective or unsuccessful. Okay, and then you want to define activation energy. The symbol is EA as the minimum energy required for a collision to be effective. Okay, now most of the things that we're going to learn in this topic is already something that you have covered in O-level. It's just that you want to elevate the explanation. There are some terms that you need to use, like collision, the frequency of collision, the successful collision, and a few others, which you will look at later on. So the collision theory says that reactions can only occur when collisions take place between particles that have enough energy or sufficient energy. It's worth to know that all the particles, the molecules, ions, compounds, all these species have a certain amount of energy. Okay, there is no molecule or no particle that have zero energy in this world, right? Everyone will have some sort of energy. And in order for reaction to take place, you need to have enough energy, and then later on there's a second factor to it. So this minimum energy is called activation energy, because in a reaction, you will first break the bonds of your reactants, and then you want to form a new bonds in the product. In order for this to happen, of course, you need some sort of energy. Okay, you cannot just expect that, oh, you add reactant 1 with reactant 2 and then you expect them to react like that. No, in reality, down to the microscopic level, there are a few factors that you need to take into account in order for a reaction to happen. Okay, even collisions alone, just because one reactant meets the other reactant doesn't mean reaction will happen. Okay, it's like the same idea of one person meeting another person. They don't necessarily have chemistry straight away. They might meet each other and then don't like each other, and then they go off and, you know, not have any chemistry or reaction together, if you put it like that. Okay. So the activation energy is the minimum energy which particles need to have in order to collide to start a reaction. So that's the definition of activation energy, which I think you have come across this definition already. Okay. In an energy profile diagram, this is called an energy profile diagram, where you have the energy of your reactants. Okay. And then over time, there will be like a hill, and then it falls down to the products. Okay, that's for exothermic. For endothermic, the energy of the reactants is way below the energy of your product. So you start all the way from the bottom, but not at zero, because as I said, everyone must have some sort of energy. Okay, you can't have zero energy. So as you go up, this this slope is your minimum energy. Okay, if you can overcome this slope, just like how you can overcome the challenge in your life, then you can become turn into products. Okay, then you can do anything. So the activation energy for your exothermic and endothermic is usually the first hill or the first slope. Okay, so that's why it's labeled here. Don't get confused with activation energy and enthalpy change. Okay, so the enthalpy change of reactants and products, since it's exothermic, it's going down. It's here in the red arrow. Okay, enthalpy change of endothermic is between the reactants and the products. For endothermic reaction, you can see it now being drawn in the red arrow. Okay, so you may notice that the activation energy of an exothermic reaction is smaller than the activation energy of endothermic reaction. Okay, I wouldn't be surprised because our energy of reactants or our enthalpy of reactants is higher than the products. Okay, so that means it is relatively easier for an exothermic reaction to happen compared to endothermic, as you would expect, right? Endothermic needs to take in energy first, but exothermic doesn't always 100% happen spontaneously. You need to climb up the hill first. The symbol for activation energy is E with a small letter A, subscript A. Okay, that stands for activation energy. Right. Maybe we can write down the EA activation energy in exothermic reaction is generally, okay, that means maybe most of the time it's true, okay, is generally smaller than in endothermic reaction. Okay, so that's it. If you know the definition of exothermic reaction and you know how to identify them in an energy profile diagram, okay, so this is called an energy profile diagram, then you should be okay. Next is looking at collision theory. Okay, so this collision theory is saying that in order for reactants to react with each other, the particles, either we're talking about atoms, ions, or molecules, must fulfill these two requirements. First, it needs to collide in the correct orientation. That means they have to meet at the right angle. Okay, the molecules have to hit each other at the right angle. So if they can do this, then you will have collision, okay, successful collision. Secondly, they need to have enough energy, and this energy is the activation energy. Activation energy will be different for each reaction. Okay, different reaction, different activation energy. Some reaction would have a higher activation energy, which is the case why sometimes we need to heat our reaction or supply energy in other forms like light, for example, or sound energy. So that's the activation energy, okay? So particles here is referring to any species of reactants, whether your reactants are between ions, between molecules, or atoms and molecules, okay? So it's not as easy as I'm mixing reactant A and then reactant B, and I expect all of them to react. Now, some of them may react, okay, as long as they fulfill these two conditions. Collision at the correct orientation, and then secondly, activation energy. Okay. Right, so what are the two types of collisions? We won't be talking much about the orientation that is not mentioned in your syllabus, but we do want to focus on the types of collision. So in your learning objective, they use the word effective and non-effective. Okay, so I suggest you to stick to these two terms using effective or non-effective collision. Well, it's also not wrong to use unsuccessful and successful collision. Okay, it's not all collision will react with, sorry, it's not all types of collisions will end up as a reaction. Only successful collisions will form products. Okay, so what do we mean by this non-effective, ineffective, or unsuccessful? This is when reactant particles collide and then bounce off each other without changing. So that means no reaction occurring. That's it, simply as that. Successful collision is when reactant particles have enough energy to react and then they change into products. So this is where reaction is happening. Okay, in other words, there is reaction here in the successful collision or effective collision, whereas in the unsuccessful collision or ineffective or non-effective, there is no reaction. They hit each other, but they don't turn into products. What are the reasons for that? Well, there could be many reasons. Maybe they don't have enough energy to react, minimum energy. Maybe they're not hitting each other at the right angle. Okay, so the diagram is showing you what happens at A, which is an unsuccessful collision. So after they meet, they break away, they are still the same original reactant. Whereas in B, after they meet, they react and then they leave to become a different person, which is a new product. All right, so that is all for your activation energy and your collision theory. Next, I want to talk about what we call Maxwell-Boltzmann distribution. Now, a Maxwell-Boltzmann distribution is a graph that shows how the energy of molecules are being spread out. Okay. The learning objective for this one is to sketch and use Boltzmann distribution to explain the significance of activation energy. Okay, so now we're looking at activation energy in terms of Maxwell-Boltzmann graph or Maxwell-Boltzmann distribution. Before I show you the graph, you need to know that molecules have different energy. As I was saying just now, there isn't any molecule that doesn't have any energy at all. Okay, in this world, even though the molecules look like it's not moving, it possesses some sort of energy, like even at a very low amount of energy, but still there's energy. Okay, it's also worth noting that different molecules of the same type, okay, have different speed, different energy. Okay, so when they have different energy, they move at different speed. I have a video. I'm not sure if you're able to see that. If you can just compare these particles, some of them are moving really fast, some of them are moving slow. Okay, I don't know if you can see that, but in reality, that's true about any particles or molecules as well. Okay, they don't have the same amount of energy. Some have low, some have really, really high, and some mostly in the middle. Okay, so that's what I was saying here, that they do not possess all the same amount of energy, some small, some large, and mostly in between. Right? So this is the function of Maxwell-Boltzmann distribution, because it shows the spread or the distribution of energies that molecules of either a gas or liquid have at a particular temperature. So this Maxwell-Boltzmann distribution only applies to gas and liquid, okay? Actually, mostly gas, but liquid can also be applied, right? As for solid, just because they're not moving doesn't mean they don't have energy, but it's difficult to measure their energy, okay, because they're intact. So this is not yet. As I said, the graph only applies to gas, but the conclusions we draw can be applied to reactions involving liquids as well. Okay, so just remember the area under the curve is the total number of particles present in a particular container. Okay, so say I have a container of oxygen gas, right? And then I am able to plot I am able to calculate the speed or the energy of each oxygen molecules in my container. And then when I plot them, okay, different molecules, different energy, some really high, some really small. And when I plot all the energy of all my oxygen molecules in the container that I was talking about earlier, I should get a distribution that looks like this. And this is what we call a Maxwell distribution. Okay, there are a few things to note. At zero energy, as I said, there is no particle or no molecule that would have zero energy in this world. Everything will have some sort, everyone will have some sort of energy. Okay, so it starts from zero, and then in the middle, so this is the area of like low energy. And then in the middle, that's the peak, that's the highest. So we call this the most probable energy. That means this is the energy value that a lot of the particles have. So that means a lot of particles, majority of the particles have energy value between this range, okay, whatever that number is there, right? And then at the end, this is the region of higher energy. There are few, and of course, the higher the energy, the lesser the number of particles will be, okay? So first things first, I should have introduced to you the X and Y axis. The Y axis is the number of particles, sometimes called the frequency, okay? The higher your graph is, the bigger the number of particles. The lower your graph is, the smaller the number of particles, or we say the smaller the frequency of the particles. And then on the X-axis is the energy. So there's no number for the energy, okay? Usually, how do we find the energy of a molecule? We look at the speed. If it moves really fast, then the energy is really high. If it moves really slow, the energy is also small. Now, another thing to notice is that the energy distribution should not touch X, because if you touch X, that means there is, the maximum energy of a molecule. Okay, so, and we don't know that, right? There is no, in theory, there's no maximum energy for molecules. They can travel really, really fast, super fast at the speed of light, in theory. Okay, so just draw it as a tail. Okay, it tails off, but never touch zero. Never touch x-axis. Never meet the x-axis. And then another thing is that it goes through the origin. Okay. As mentioned earlier on from the previous slide, the area under the curve represents the total number of particles. Okay, so here, this tells you the total number of particles in my container. Okay, in this Maxwell Boltzmann distribution curve, my activation energy is usually towards the tail of the graph. Okay, not too far out, because if you draw it too far out, that means your activation energy is really high. All right, but the most important thing is my activation energy must be somewhere after the hill. That's the most probable energy. Okay, so what this activation energy is saying, okay, as we said just now, when molecules have energy exactly the same as the activation energy or above, bigger than the activation energy, they can react or reaction can happen. So that means the number of molecules that can react is only this shaded region, because these are the number of particles that have energy exactly at EA or above. All right. If you are below activation energy, you have energy, yes, but you don't have enough energy. You don't meet the minimum requirement for a reaction to happen. So you can see that in a reaction, there's only a small proportion or a small number of molecules that can overcome the activation energy. Okay, so that's what this label is. Only a few particles have energy greater than the activation energy, or sometimes they use the word only a small proportion. Okay, have energy greater than activation energy. So that means if they have energy greater than, equals to, or greater than, okay, activation energy, effective collision can happen. And what do we know when effective collision happens? It can cause chemical change. So this is reaction. Reaction is happening. Okay. So if you want to find the area, if you want to know the number of molecules, you have to find the area of the shaded region. Okay. Now the other side, I'm going to use a different number, okay, a different color. So this side is pink or red. Okay. We say that these particles, I don't have space, these particles can collide, but ineffectively or non-effective collision. These particles will collide non-effectively. So that means not enough energy to cause a chemical reaction. In other words, no reaction is happening, no chemical reaction is happening. Okay, so hold on to this graph first because it will come in handy later on. Okay, moving on from the Maxwell-Boltzmann distribution, we now move on to the rate of reaction. The next learning objective is to use experimental data to calculate the rate of reaction. Okay, usually we use graph. Reaction kinetics is the study of the rate of a chemical reaction and the factors that affect it. Okay, so I've already talked about this at the intro just now. The definition of rate of reaction is the change in concentration of a substance. Substance here can be reactants or products in unit time. Its usual units is mole per dm cube per second. But again, follow the question. Sometimes they use minute, so you will use mole per dm cube per minute. But the SI unit for time is second. Okay, so it's best if they don't mention it in the question, best to always leave it in mole per dm cube per second. Okay, by definition, rate is equals to change in amount, whether you're talking about concentration or mole, of reactants or products over time. So if you want to work out the units, it will be concentration is in mole per dm cube. Okay, I'll just write it here. Mole per dm cube for concentration, and then for time is seconds. So if you have mole per dm cube over second, you bring up the S, it becomes mole dm minus 3 S minus 1. So that's how I got my unit. Okay. All right. So how can we find the rate? Oh, before I forget, rate is also proportional to time, inversely proportional to time. So you can see here, rate is inversely proportional to time. If the time of your reaction is long, we say, if it takes long for the reaction to finish, okay, long time, so we say that the rate is slow. If the reaction takes a short time to be completed, we say it has a high rate of reaction. Okay, so rate and time are inversely proportional. When time is big, rate is small. Okay, next is looking at the graph. Okay, usually the easiest way to monitor the course of a reaction, that means to monitor the progress of the reaction, we look at plotting concentration time graph. Okay, so concentration is in mole per dm cube, and then time can be in second or in minutes. Okay, this is a typical, I think you have seen concentration time graph before. Okay, and without looking at the equation, I can already tell that this graph belongs to a reactant because I'm starting at a certain amount, okay, and then over time my reactant is decreasing until I eventually reach a constant line, a straight line, or a plateau. A plateau is just a line that's not changing. Okay, so to find the rate of reaction, by definition, is change in concentration over change in time. That is your delta Y over delta X. I don't know if this rings a bell to you. Change in Y over change in X is the gradient of the graph. Okay, now since it's not a straight line, it's a curve. How do we find the gradient of a curve? You have to draw a line, a tangent, okay, so a line that is tangential to the point of interest. Say if you want to know the gradient at t equals to 0, you have to draw a line that is tangential. It's a tangent. Please don't ask me to explain what a tangent is. I hope everyone knows what a tangent is, okay? So that is the tangent at t equals to 0. Say this is maybe 20 minutes, okay? 20 seconds. 20 seconds, okay? So that's 20 seconds at that point. And if I want to find the rate at that point, I cannot just assume that the rate is the same. Okay, the rate is changing because the gradient is changing. So I need to draw again another tangent at t equals to 0. Well, that's not a great tangent, but you get what I mean, right? And each tangent is showing you or telling you the rate of reaction at different time. Okay. Right, so when a graph of concentration of reactant or product is plotted versus time, the gradient of the curve is the rate of reaction. The initial rate is the rate at the start of the reaction where it is fastest. Okay, so I'm going to explain why the rate of reaction is fastest at the beginning of the reaction. The reason for this is because at the start, you have a lot of reactants. So the rate is really fast, really crazy. But over time, as you slowly start to use up your reactants, then your rate is becoming slow until eventually you run out of reactants to react, in which case your rate is 0. Okay, that means your reaction has stopped. If rate is 0, that means there's no reaction happening. Okay, I hope that is clear. Here is an example of a concentration time graph of a product. How do I know that? Because at the start of the reaction, I have 0 concentration. That means I have nothing. So at the start of the reaction, we usually don't have any product, right? So over time, I'm producing product and then starts to decrease gently until I reach a constant horizontal line, in which case if you find the gradient of a horizontal line, the gradient is 0. That means the rate is 0. There is no reaction happening anymore. Okay, now that's the concentration time graph. What can I do to prove my explanation that I say just now? At the start of the reaction, the rate is really fast and then it slows down over time. Okay, I can use gradient, I can use calculation to prove that over time my rate is decreasing. Okay, without doing calculation, you can already see the triangle represents the gradient. Okay, so there is a tangent drawn at t equals to 0, and then there's they draw the triangle to show how you find the tangent. Okay, but I'll just look at the line. Now look at this line at the start, and then another line, and then that line. And can you see that my gradient is big at the start? It is steep at the start, and over time it becomes gentler and gentler. Okay, well, gentle is less steep lah, right? So if you can see it visually, that the gradient is going from very steep to gentle, that is already enough of proof to tell you that the rate is also decreasing over time. If you're not convinced, then you would have to do calculation. Okay, right. So this is a sketch showing you the concentration time graph of reactants on the left. You start with something and then the reaction stops when you no longer have any reactants left. When your reactants is at 0, the reaction stops. Or when it is at a flat line, constant horizontal line. As for products, you start from something and then over time, you will then reach a constant horizontal line, which tells you that the reaction has stopped. Now, here we are talking about irreversible reaction, a reaction that only goes in one direction. Okay, please do not get this confused with equilibrium. Okay, so to explain what I was saying just now in words and for you to write it down in your notes, reactions start off quickly at the start because of the higher possibility of collisions. Sorry. Okay, so more reactants present, more chances of effective collisions, therefore more reaction, okay, or faster reaction. Over time, the gradient decreases, or we say it becomes gentle or less steep. So that means rate of reaction decreases over time. It gets slower and slower. The reason for this is because you now have less and less reactants to collide. Okay, so now your chances of collision is smaller. Okay, when gradient is 0, the rate of reaction is 0. The reaction has stopped. So that this is what I was telling you as well just now. Moving on, Oh, now we are looking at example. Okay, so example 1, calculate the rate of reaction for 0.440 grams of ethyl ethanoate formed in 1 minute from a reaction mixture of volume 400 centimeter cube. Okay, so the rate of reaction is best when you do it graphically, okay, because you can see that you can find the rate of reaction at different time or different concentration, okay? But this one, just for the purpose of practicing our formula, rate is equals to change in concentration, that's concentration. Delta means change, okay, over time. The question also did not mention the units, but I would like you to leave your units in mole per dm cube per second. Okay, so first hint for you is to find the concentration of ethyl ethanoate. Once you've found the concentration, correct concentration, remember it has to be in mole per dm cube. You've got mass here, so that means you need to change that to mole, okay, over time in seconds. Okay, so please work that out, and then you can check the answer of your numerical answer in the forms later on. Okay, it's a really simple exercise. This is the rate. This is the graph of a concentration time. Concentration time graph for the reaction isomerization of cyclopropane. Okay, so if you want to study or monitor the rate of reaction, you can either plot the concentration of reactants over time or plot the concentration of products over time. Here they have plotted the concentration of reactants, okay, because you start from something and you're decreasing over time. So it looks complicated, but actually there's just if you just look at one point at a time, then you'll be fine. Okay, so let's have a look at point 1. Point 1 is to find the rate at concentration of 1.5. So 1.5 is here, and that is your initial rate of reaction. Okay, so this is also called initial rate of reaction. Initial rate of reaction is at t equals to 0. Now, some of you, I have one student asking, isn't t equals to 0 means at this, like, you haven't started the reaction, right? Shouldn't the rate be 0? Now, when they ask you for initial rate of reaction, it means what is the rate at the moment the reaction has started. So you have to draw a tangent at t equals to 0, and it will not be 0. Okay, so let's have a look. At t equals to 0, so I'm going to pretend that is a tangent at t equals to 0. So I'm just extending the line. Okay, and then I will find the gradient of this line I have just drawn, because gradient is change in y over change in x. If you look at this graph, change in y is the change in the concentration of cyclopropane over the change in time. Remember, rate is equals to change in concentration over time. So you can find the rate of the reaction initially to be 1 times 10 to the power of minus 3. And then you repeat this process at point 2. I'm going to use blue now. At point 2, they want to find the rate of reaction at concentration 1.0. So 1.0 is here, concentration. Okay, so I need to draw a tangent line that just touches the concentration 1.0. So that's my 0.2. Okay. So again, I take the gradient of 0.2, assuming this is a nice triangle, okay? And it turns out that my gradient is 6.67 times 10 to the power of -4 mole per dm cube per square, okay? And then I repeat this process for 0.3, which is the rate at concentration 0.5. So concentration, I should be looking at the y-axis, and 0.5 is, sorry, is somewhere here, okay? So that's why we draw a tangent to this line at 0.3, looking something like that, okay? Now, even without doing the calculation, if you just compare purple line, blue line, and lastly, the red line, you can already see that the gradient is getting less steep. Yeah, the purple line is showing you the steepest gradient, and the red line is showing you the least steep gradient, or the gentlest gradient, right? And if that doesn't convince you, you can look at the numbers. Look at the numbers. At the start of the reaction, your rate is 1 times 10 to the power of -3. And then it decreases to 6.67 times 10 to the power of -4, and it decreases even further, 3.3 times 10 to the power of -4. That means rate of reaction decreases over time. And this is true for all reactions, not just the isomerization of cyclopropane. Okay, so please, this calculation of rate of reaction graphically is probably not required of you in AS, but you definitely need to know this and build on this for your A2 later on. Okay, right. What if now I change my graph instead of what do I have here? Oh, okay. So this is still showing you the concentration time graph. Okay, it's showing you that the concentration of product is increasing. Okay, it increases with time. And if you want to learn about the rate of reaction, same thing, you draw the tangent initially at t equals to 0, and then maybe at t equals to 20, and then at t equals to 40, you can see that the line are getting gentler and gentler. All right, that shows you the rate of reaction is decreasing over time. Okay. Moving away from all those graphicals and calculation, we now move on to the explanation qualitatively. Okay, that means you're not using number, you're just using explanation. In terms of frequency of effective collisions, that means in A level, you must mention this in your answer. You must talk about collisions. It's not enough to say, oh, you increase the concentration, there are now more molecules of reactants, so rate is faster. No, you have to mention about this collision. Okay, effect of concentration and pressure changes on the rate of reaction. Okay, you already know that the factors that can affect the rate of reactions are concentration, which we will look at, and pressure. Concentration and pressure are closely related, right? Pressure is just basically concentration for gases. Surface area, you already know that increasing surface area will increases the rate of reaction, but it is not being mentioned in your syllabus, so we will not cover it. Okay. Temperature will affect the rate of your reaction as well. And lastly, catalyst, right? Remember, rate of reaction and equilibrium, there's a difference. Catalyst will not affect or will not change your equilibrium. Okay. Right, concentration. What happens at higher concentration, whether you're talking about liquid or you're talking about the gas, in which case we should refer to it as pressure, we now have more particles. Yes, we agree. We now have more reactant particles. Because you have more reactant particles, the probability of collision is also higher. Yes? Now, if the probability of the frequency of collision is higher, then the probability of effective collisions or successful collisions will also be higher. So this is the reason why increasing concentration increases your rate of reaction. More effective collisions, more higher rate. Okay. Basically, that's just it. You just have to learn how to explain them, right? Moving on to pressure, as I said just now, pressure and concentration works the same way. It's just that pressure is more relevant and applicable to gases, whereas concentration can be in liquids or in gas, right? So an increase in pressure, well, there are two scenarios where our pressure can be increased. First is if we increase, looking at this diagram, if we increase the number of particles. So that's the same like increasing the concentration, right? If we increase the number of moles or if we increase the number of molecules in the same volume of a container, right? So if I look at A and B, between A and B, the pressure is higher in B, okay? All right. There is another scenario how you can increase your pressure by keeping the number of molecules the same. You have 1, 2, 3, 4, 5, 6. 6 on both sides. Okay, so they have the same number of molecules, but this time you reduce the volume. You make the container smaller. And between C and D, D has a higher pressure. Between A and B, B has a higher pressure. Okay, so we're going to look, it looks like, you know, B and D, the most common thing about these two is that there are more molecules at a much smaller or confined space, or we say that there is not much space between the molecules. Okay, you can, I think we all can agree that B and D does not have a lot of space around the molecules. Okay, so the explanation: an increase in pressure in reactions that involve gases has the same effect as an increased concentration of solutions. Okay, when the pressure is increased, the molecules have less space. If they have less space between them, that means the proportion of frequency will be higher. That means the probability of effective collisions will increase as well. Please take note, oops, collision does not equals to effective collision. Okay, collision, they just hit each other. Whether or not they result in a reaction, it's not mentioned, we can't tell. But effective collision, we know that there is a reaction for sure. Reaction is happening. If we just say collision, we don't know if there's reaction or not, right? So my suggestion is you must mention this too. Now that there are less space between your molecules, the frequency of collision will increase, which results in the increase of effective collision. That's how you explain why the rate of reaction increases as pressure is increased. Okay, moving on. Again, here is another diagram to show you how increasing pressure can increase the rate of reaction. Okay, same thing, so I will not go through it. This is the one that is not mentioned in your syllabus, so I'll just show you the diagram quickly. This is when you have a low surface area. This is when you have a high surface area, and you can see now that the green molecules and the red atoms have higher chances of colliding with each other. Therefore, the effective collision will also be higher. Full stop. Done. Next is the effect of temperature on the rate of reaction. Okay. The learning objective is to explain qualitatively in terms both of the Boltzmann distribution and of frequency of effective collisions, the effect of temperature change on the rate of reaction. Okay, so I think in O level, when you are asked to explain why increase in temperature increases the rate of reaction, everyone is so quick to answer kinetic energy increases. It's true, but that is the less important point. In A level, there is another point that is far more important and far more significant. Usually choosing this answer will give you a full mark. Okay, it's the safest answer. If you write down kinetic energy, you will probably only get not half, like partial mark. Okay, so that's why I have put them in asterisk. Okay, increase in temperature, yes, your kinetic particle increases. All right, that means your particles now move fast. That means there will be a lot of collisions. Yes, the frequency of collision will increase. Okay, now if the frequency of collision increases, this also increases the successful collision or effective collision. That's why the rate of reaction increases. Done. But that is not so important. This is the less or least important factor. In order to understand the most important factor to explain why the increase in temperature increases the rate of reaction is when we look at the Boltzmann distribution graph or Boltzmann distribution diagram here. Okay, so the blue graph, the blue dotted graph is the Boltzmann distribution of the energy of my molecules at room temperature, for example. Okay, so I will say this is at room temperature. And then at 25 plus 10, 35, okay, at 35 degrees, that's my Boltzmann distribution or Boltzmann graph in purple. Okay, now let's have a look at the blue one first at room temperature. Okay, remember just now when I introduced Boltzmann distribution, Boltzmann Maxwell distribution, there is this point called the activation energy that's not labeled, EA. So activation energy is the minimum energy required for particles or molecules to have in order to result in a reaction, okay? Or in order to change them into products. If I look at the blue graph, the proportion of molecule that can result in a reaction and effective collision is this amount. Okay, just that small part, right? So this is the proportion. I suggest you to use color pen for this one, okay? the proportion of molecules that can react and turn into products. Right? Now, if I increase the temperature, the energy of my molecules will increase. Okay? Now, the Boltzmann Maxwell distribution will also change. My graph will be shifted to the right because the right direction is in the direction of increasing energy. Okay, but the shape is generally still the same. I still have that like hill or slope, and then it starts to tail off, but never touching the x-axis. Okay, so this is what happens when temperature increases. As you would imagine, my energy would be bigger, so my graph would be shifted to the right in the direction of increasing energy. Okay, now another thing that is most important is we now look at the area under the curve bigger than EA. Can you see this region? The purple region. Yeah. Okay, so I'm going to shade that first. Can you see now that this area is bigger than the blue shaded area? This means that there are now more particles or bigger proportion of particles having energy equals to or bigger than activation energy. I now have more particles that can react, that can result in changing into products. Okay, so take a different color. I'm going to use purple because it matches with the graph, and then I'm just going to shade them like that, so you can still see between the purple and the blue. Now, even without calculation, just by looking at it, you can tell already that the area of the purple shaded is bigger than the area that's shaded in blue, right? So the explanation is that there is now an increase in reaction rate because greater proportion of molecules that have energy equal to or greater than the activation energy. So these molecules now that are having energy equals to or above activation energy can collide and result in effective collision. Okay, so that's crucial. Kinetic energy is the second point and it's the less important point. So what happens if you increase temperature? It will be shifted to the right. So I have already mentioned that to you. The other two factors I haven't mentioned to you. The peak is now lower. Okay, so you start at a bigger number and then it decreases down. And the tail is also higher. It's above the blue tail. The reason for this is that if your graph is going down, it needs to be spread out horizontally. Okay, now if that doesn't make sense to you, just remember these features. Okay, and the idea is the area under the graph of the blue and the area under the graph of the purple must be the same. You cannot change the area because area under the graph tells you the number of molecules. You are only changing the temperature. So your number of molecules should be the same at room temperature or at higher temperature. Okay, this said, if you decrease the temperature, say now I decrease the temperature to 10 degrees Celsius. What happens? It's the opposite. My graph shifts to the left, my peak becomes higher, and my tail becomes lower. All right, can you see that? Okay, so remember these three factors. Don't just draw simply, you shift it and then you just simply draw it. You must remember these features. Okay, as you increase the temperature, the peak is now at a lower point or at a lower value. It shifts to the right. Okay, it was initially at this energy value and then now it's somewhere here. Okay, the tail is also higher than your original graph. Okay, right, so we go back to the explanation, part 1, the one with the asterisk, that I really emphasize on the importance of this explanation. Okay, so the reason why the reason why rate increases as temperature increases is because the proportion of particles with energy greater than activation energy increases. So this whole thing is or must be highlighted. Okay, you cannot leave that out in your answer. Must full complete answer like that. Okay, now that you have more particles having enough energy, your collision will increase. Successful collisions will increase, therefore your rate increases. Okay, I hope that explains the new explanation that you just learned. So it doesn't change anything that you have learned previously in O-level. That still applies, but it just now becomes less important. Okay, last one. Let's finish this all in one session. Okay, the effect of catalysts on the rate of reaction. Okay, explain that in the presence of a catalyst, a reaction has different mechanism, i.e. one of lower activation energy. Construct and interpret this in a reaction pathway diagram for a reaction that has that has a catalyst and that's one without a catalyst. Okay, right, what does catalyst do? Catalyst increases the reaction rates without getting used up. How does catalyst increases the rate of reaction? By providing an alternative route or mechanism with a lower activation energy. This point is important, lower activation energy. Okay, so the learning objective just now wants us to show this in energy profile diagram. So we go back to our energy profile diagram. Okay, here my purple is uncatalyzed reaction. So this must be an exothermic reaction because the enthalpy or the energy of my reactants is higher than my products. Okay, so what happens? As usual, reactants will need to obtain a minimum amount of energy, which is the peak of my graph. Once I can overcome this activation energy, it converts smoothly into products. That's my uncatalyzed reaction. With a catalyst, if I add catalyst, what happens? By definition, what catalyst does is by providing an alternative route. So I now have a different route, and this route has a lower activation energy. So if you look in blue, can you see the peak of blue is now lower than the peak of purple graph? Okay, so my activation energy was this much for without catalyst, but with catalyst, now it's lowered down to that much. Okay, so this is what it means to provide an alternative pathway that has a lower activation energy. Okay, so that's why your reactants, that's why your rate increases, because now you have lower activation energy and more energy can now result in effective collision, which is a reaction or turning into products. Okay. Right, so catalyzed reaction with an activation energy lower than the uncatalyzed reaction. So uncatalyzed reaction means just a normal reaction. Okay, so instead of writing down EA new, maybe you can change it to EA catalyzed. That means that there is a catalyst. Okay, EA cat. So this diagram just shows the function of a catalyst already, right? What if we have an endothermic reaction? So endothermic reaction, the energy or the enthalpy of the reactants is lower than the energy of products. Okay, so same thing. The purple is my pathway diagram of an uncatalyzed reaction. Okay, so I'll just label that EA of uncatalyzed reaction. And with the catalyst, I should have another pathway, a different route with a lower activation energy, but I cannot change the energy of the reactants and the energy of products. Okay, I'm only changing the activation energy. So that means my activation energy is now this much. EA cat. Please color coordinate them. Okay, otherwise you will get confused. So can you see that now my activation energy of the catalyzed reaction is lower than the uncatalyzed reaction? Okay, so that's the pathway diagram. So that means now that we have a much lower energy, it's easier to overcome this activation energy. A bigger proportion of molecules, reactant molecules, will have energy equals to or bigger than the activation energy. All right, last. Explain the presence of a catalyst. Explain this catalytic effect in terms of the Boltzmann distribution. Okay, so we look at the Boltzmann distribution. Okay. Maybe I use the word dark purple and light purple. Okay. But later I'll change the color. I'll change the color. Maybe I'll change it to, what color should I change it? Okay, later lah, huh? Right. So this is the Boltzmann distribution in purple of my reaction. Okay, the activation energy is here. EA of a normal reaction, no catalyst. Okay, and then the proportion of molecule that can react is this much. Okay, so I label that as the proportion of molecules that have energy equals to or higher than activation energy. Okay, so this is the proportion of molecules. This is the number of molecules that can bring out a reaction. Okay, that can make a reaction happen. With catalyst, remember, catalyst now provides an alternative pathway that reduces. It means that it decreases the value of activation energy. And in this diagram, if I decrease the energy of activation, if I decrease the activation energy, my new EA, maybe I'll use blue so you can see, is now here, EA catalyst, because smaller number, right? Remember, my axis is going from 0 to a bigger number. So if I make the activation energy smaller, then my line has to be moving to the left. Okay, so my activation energy catalyst is there. And so the proportion of molecules that can react is this much. Can you see that the blue shaded area is bigger than the purple shaded area? Okay. So that means EA catalyst is, so catalyst lower the EA here or here. That means more particles have energy equal to or greater than EA. Okay, so the explanation is here. If the activation energy is lower, that means it is shifted to the left, it is moved to the left. More particles will have energy equals to or bigger than EA. Well, the symbol there is equals to, bigger than. So there will be a higher frequency of effective collisions. The reaction will be faster. That's it. That's all you have to explain. But to show it graphically, you have to move your EA. Okay, so label your EA. This one, proportion of molecules that have energy greater than the activation energy, EA act and EA. Okay, maybe change it to EA cat and just EA. Okay, EA cat means catalyze. Okay, that's it. Really, that's it for this topic. We are done. All right, so I hope, even though I was going really, really fast, please go over your notes again. It's a short one. Also, this topic is not big for AS. It will be a bigger topic in A2. It usually accompanies other topic, like they combine the question from kinetics with energetics, which is, I know, not energetics, with equilibrium. Okay, so when they ask you to explain what is the implication of increasing the temperature, what's the effect on the equilibria, what's the effect on the kinetics, that is the rate of reaction. So it's more like that. Okay, but the most important thing is that you understand the Maxwell-Boltzmann distribution. You also know what happens when catalyst is added, because those are the only two things that are new to you. And of course, calculation of the rate of reaction, which is, again, not so crucial for you in AS, but it will be in A2, and it's worth having a visit now. Okay, right. As usual, please fill in the forms for your post-test questionnaire. Assalamu alaikum and thank you.